This is Bob Capetta from the University of Illinois at Chicago, and here is another example on partial fractions, partial fraction expansion. So here's our problem, integral of 3x minus 5 over 4x squared minus 25. You may recognize that the denominator is a difference of two perfect squares. That's factorable. 4x squared minus 25 is 2x minus 5 times 2x plus 5. When the denominator is factorable, partial fraction expansion may be our best strategy. So let's rewrite that with the factored denominator. So 4x squared minus 25 becomes 2x minus 5 times 2x plus 5. We want to write this rational function as a sum of two rational functions, as a sum of two fractions. The first fraction over 2x minus 5 plus the second fraction over 2x plus 5. That's our general strategy. So we're going to call the numerators a and b. We're going to rewrite that fraction as a over 2x minus 5 plus b over 2x plus 5. And our strategy is going to be to determine what a and b are using algebra. So we're certainly capable of doing that. I'm going to go ahead and rewrite this thing vertically. So 3x minus 5 equals a over 2x minus 5 plus b over 2x plus 5. And now our goal is to build a common denominator, which will be 2x minus 5 times 2x plus 5. So we want each of these fractions to have the denominator 2x minus 5 times 2x plus 5. And you can see the top one already has that. Well, if I want the middle fraction to have 2x minus 5 times 2x plus 5, you'll notice it was 2x minus 5 before. I had to multiply 2x plus 5 here, so I'm going to need to multiply 2x plus 5 on top to keep that balanced. Here the 2x plus 5 was there before. I had to multiply by 2x minus 5 on the bottom. So multiply the top by 2x minus 5. So notice a was there before, multiplying by 2x plus 5. If they would cancel, I get a over 2x minus 5, what I have here. But since I multiplied the bottom by 2x plus 5, multiply the top by 2x plus 5. In our second example, we want the denominator to be 2x minus 5 times 2x plus 5. 2x plus 5 was there, multiply the bottom by 2x minus 5, multiply the top by 2x minus 5. If those would cancel, I get b over 2x plus 5. You can see those are equivalent fractions. So our next move is to distribute 2ax plus 5a, 2bx minus 5b, as you can see. So we have common denominators for all of these things, and our goal is to solve for a and b. And the question is, how are we going to do that? Here's where we are now. 3x minus 5 over this denominator is 2ax plus 5a over this denominator plus 2bx minus 5b over that denominator. We have a common denominator. We can write this as a single fraction. Hence 2ax plus 5a plus 2bx minus 5b over that common denominator. Then we want to collect our like terms. So the x terms, 2ax plus 2bx up here, x terms, constant terms, 5a minus 5b. Rewriting that way, we now see all of the x terms are together, all of the constant terms are together. How is that going to help us solve for a and b? Well, factoring the x out of those two, we get 2a plus 2b times x, constant terms 5a minus 5b. Look at the first and the last fraction. Something x plus something. Over here, something x plus something. The coefficient of x here is 2a plus 2b. Coefficient of x here is 3. Therefore, 2a plus 2b has to be 3. In this case, 5a minus 5b constant term has to match the constant term here, negative 5. So we need to use techniques of algebra to solve that system of equations. 2a plus 2b has to be 3. 5a minus 5b has to be negative 5. And this time I'm going to use elimination of variables to solve for those things. So there's my two equations. I'm going to write them vertically. 2a plus 2b is 3, 5a minus 5b is negative 5. I want to eliminate all of the variables. I'm going to multiply the first equation by something and the second equation by something else so that one of the variables will disappear. What did I decide to do? Multiply the first equation by 5, second equation by -2. That way, 5 times 2a is 10a, -2 times 5a is -10a, and the a's will cancel. 5 times 2a, 10a, 5 times 2b, 10b, 5 times 3, 15, -2 times 5a, -10a, -2 times -5b, +10b, -2 times -5, +10. So you'll notice when I add these together, 10a plus -10a gives me 0a. 10b plus 10b gives me 20b. 15 and 10 gives me 25. The good news is all of the a's have vanished, so I only have one variable and I can solve for that. So 20b is 25, dividing by 20b is 25 over 20. Reducing that fraction, dividing top and bottom by 5, we get 5/4. Now how are we going to get a? You'll notice I have two equations over here. I can substitute the b of 5/4 in one of those equations to go ahead and solve for a. So it's up to you to decide. I went ahead and used the second one. 5a minus 5b is -5. Replace b with 5/4. So b becomes 5/4 since b is 5/4. 5a minus 5 times 5/4 is -5. 5 times 5/4 is 25/4. Adding 25/4 to both sides, we get 5a is -5 plus 25/4. How do we add these fractions? -5 times 4 is -20. 25 times 1, the denominator here is 1. 25 times 1 is 25. -20 plus 25 is 5. Denominator is 1 times 4 is 4, and we get 5/4 there. So we have 5a is 5/4. Divide both sides by 5. Maybe that's obvious that a is a quarter. If not, I'll go ahead and spell it out for you. Dividing both sides by 5, a is 5/4 divided by 5. Divided by 5, 5/4 times a fifth, and I get a is a quarter. So we did our work. B is 5/4, a is 1/4. We've got to go back to our original to see what a and b represented. So we had 3x minus 5 over 4x squared minus 25 is a over 2x minus 5 plus b over 2x plus 5. We had a as a quarter, we had b as 5/4. So if I want to integrate this, integral 3x minus 5 over 4x squared minus 25, 1/4 over 2x minus 5 plus 5/4 over 2x plus 5. The integral of the sum is the sum of the integrals. And we can pull the constant out in front. So 1/4 integral of 1 over 2x minus 5 plus 5/4 integral of 1 over 2x plus 5. And this is a job for u substitution. So we'll let u equal 2x minus 5, and maybe w equals 2x plus 5. So if I let u equal 2x minus 5, derivative with respect to x of u is the derivative with respect to x of 2x minus 5. du dx is 2. du is 2 dx. And the way I do this, I want to solve for dx. dx is du over 2. So that 2x minus 5 will be u, the dx will be du over 2. But I also need to sub on this piece. So let's let w equal 2x plus 5 and see how that works. Almost identical. W is 2x minus 5. ddx of w is ddx of 2x plus 5. ddx of w, dw dx. ddx of 2x plus 5 is 2. Solving for dx, dw is 2 dx. So dividing by 2, dw over 2 is dx. So here we go. There's our u, there's our w, and here is where the problem is currently. Replace 2x minus 5 with u. Replace dx with du over 2. Over on this side, replace 2x plus 5 with w. Replace dx with dw over 2. Pulling the 1/2 out here, this will give me 1/8 integral of 1 over w. Pulling the 1/2 out here, 5/8 integral of 1 over w. But integral of 1 over w is log, is log w. Integral of 1 over u is log u, absolute value, of course. So 1/8 integral of 1 over u log absolute u plus 5/8 integral of 1 over w log absolute w plus c. Last thing I have to do is substitute the u and the w. U is 2x minus 5. W is 2x plus 5. Plug those in, and we get 1/8 log absolute 2x minus 5 plus 5/8 log absolute 2x plus 5 plus c. And that will conclude this example.